Hello! This is a short presentation on the kinetics of scuba diving. I'm Shep Johnson. Starting off with a little bit of history, the first successful diving apparatus was the standard diving dress, as developed by the brothers Charles and John Dean in 1828. If you look at the image on your left, that's not an example of their particular thing, but of a standard diving dress kind of uniform. The first successful open circuit scuba device, one of those devices that look more reminiscent of what we think of as scuba today, was developed by a French engineering team in 1942, and they branded it as the Aqualung, also being the first to achieve commercial success with a diving apparatus. Given how equipment directly affects kinetics, it's only appropriate to do a quick run-through of a modern scuba system. The dive mask and snorkel, the dive mask is largely to be able to see underwater, a very important thing to do, and the snorkel is largely for surface swimming, so you're not using as much of your tank while scuba diving. The regulator, sometimes referred to as an octopus, as you can see on the image on your right, all those cords kind of sprawl out so it looks like a little octopus. Most important to our purposes of kinetics, the buoyancy compensator device is a vest that has internal bladders that can be filled with air. Purpose behind that later on. Submersible pressure gauge, just how much air do you have left in the tank. Your dive computer tells you the time, can also be used as a tool to indicate how much time you have left at a given depth before you need to return to the surface to prevent adverse effects. And then, your scuba fins makes you a little bit easier to swim, and wetsuits so you don't get quite as cold. A little bit more history about scuba diving. Christian J. Lambertson was the first to coin the term self-contained underwater breathing apparatus, or scuba as we better know it, when he was patenting his own system for United States Marine frogmen, so they can do underwater warfare. The most prolific of scuba training programs is the Professional Association of Diving Instructors, better known as PADI, which was founded in 1966. Just to give you an idea of how recent a lot of this activity actually is. Starting off our biomechanical concepts with buoyancy, buoyancy is an upward force exerted by a fluid that opposes the weight of a partially or fully immersed object. As we're scuba diving, this will be an immersed object. F equaling the force, the symbol rho indicating the density of the liquid, G being the gravitational constant, and V being the volume of the object. So how do we control the force of buoyancy? Well, the primary methods of control include using weights due to their density. They sink in the water faster, and they'll bring you along with it. Breathing it works both ways. When you inhale air, the air is far less dense than the water around you, causing you to rise in the water. When you exhale, that air leaves your lungs, causing your overall density to increase, making you sink further in the water. Your BCD works almost exactly the same way. By pumping air into your BCD, you increase your ability to rise in the water, but when you get rid of the air, you decrease in the water. The control of buoyancy is necessary for a couple of safety reasons, two among them being nitrogen narcosis and decompression sickness, sometimes referred to as the bends. Nitrogen narcosis has some effects that I would describe as high-like, one of them being euphoria and other inabilities to assess risk. With nitrogen narcosis, that can cause you to not be aware of how much air you have left in your tank and other surrounding dangers, so it's vitally important to prevent that. And decompression sickness is caused by a rapid ascent to the surface of the water, where the ascent is so quick that nitrogen bubbles start to form in your blood, which can lead to extraordinarily adverse effects. And good buoyancy control is necessary to improve one's ability to stay underwater. By adjusting it to be properly weighted, as we can see in the middle of the two images, it improves the trim and the overall horizontal swimming when swimming horizontally. The second of our biomechanical concepts is torque, as defined by the result of a perpendicular force acting on an object away from an axis. This causes the object to rotate around this axis. As we can see in our little equation here, sigma representing sum, F being the force applied, and d perpendicular being the distance away from the axis of rotation. This is also equal to our moment of inertia and angular acceleration. One of the interesting things about torque when swimming is one experiences torque even without moving due to what is referred to as passive torque, where due to a misalignment between one center of mass and one center of volume, forces of buoyancy and gravity are applied at different points, causing a point between the two to be the axis of rotation, creating a torque at that point. The longer the body showed that we would have more torque due to a greater distance away from the axis of rotation. As we're studying flutter kick specifically, your hip would be the axis of rotation, and your most distal toe would be the distance. At slower swimming speeds, it was found divers tend to prefer more comfortable movement patterns, so less torque in that instance, whereas in faster movement, efficiency was more desired and opted for. As we can see in our image here, it shows the kind of ranges of movement with the torques, and each of the arrows kind of pointing indicate the angular acceleration, as the moment of inertia for each limb is unassigned. Just to get a little bit more visual with it, as we can see here, free divers will use much longer fins than regular scuba divers, primarily due to the fact that free divers have a much more limited oxygen supply, just about what's in their lungs, whereas a scuba diver will have a full tank on their back. But by increasing the length of the fin, we increase the distance away from the axis of rotation, creating more torque. Drag. No, not that kind of drag. This kind of drag, the biomechanical one. Drag is defined as a force acting opposite to the relative motion of any object, moving with respect to a surrounding fluid. Kind of go through the equation. The force of drag is equal to 1/2 the density of the fluid, the symbol rho here, times the velocity squared, times the coefficient of drag, as represented by the CD, times the cross-sectional area of the object that is moving in the fluid. When you increase the area of that the fluid's being applied to, the more drag you're going to get. So how does drag apply to scuba diving? Well, most of scuba diving is just doing your best to coast through the water to use as little oxygen as possible. This drag is largely referred to as passive drag, which occurs when you're gliding through the water in a stable, streamlined position. By reducing the passive drag, more of the velocity gained when you're actively swimming is retained, causing you to travel further. On the note of passive drag, there's also kinetic drag, the active drag caused by your swimming itself. Aside from the drag you experience just from increasing your velocity in the water, the kicking of your legs also creates more turbulence in the water, resulting in areas of low pressure forming, changing the flow speeds, and ultimately increasing the drag coefficient, increasing your drag overall. Going back to our slide about buoyancy, proper trim helps improve drag by reducing the cross-sectional area of the swimmer in the desired direction. As you can see in the image, because the gentleman is swimming at a slight angle, we can there's a much larger area being applied against the water.